In this video, we will discuss section 11.10 dedicated to Taylor and Maclaurin series. Up to this point, especially in section 11.9, when we discussed representing functions as power series, we had to resort to certain arithmetic or otherwise manipulations in order to obtain a representation of a function by a series. But in general, we still don't know how to answer the question, the main question we have to deal with when discussing power series, specifically what functions have power series representations and how to find these representations. In this section, we will give a partial answer to this question by first assuming that f of x can be represented as a power series. So let's say we have a function f of x which we know can be represented as a power series. Turns out that for such a function we have the following theorem. So if a function f can be represented as f of x equals sum ck x minus a to the k, so an infinite possibly sum over the index k, and this representation of f of x must be true for x minus a absolute value less than r, for some positive r. So assuming we know this, then we can in fact determine the coefficients ck like so. We have that ck is equal to the kth derivative at the point a of f divided by k factorial, k greater than or equal to 0. So we should say here that our notation is the following. Here f with superscript k is kth derivative, and f to the 0th is equal to the function itself. So the 0th derivative of a function is the function itself. Furthermore, 0 factorial denotes 1. So this is what regards the notation in this expression. So if we substitute, so we could say that this is the statement of the theorem. But it will be useful to expand on it a little bit. So let us substitute the expression for ck into the power series. And as a result, we obtain the following expression. We see that f of x can be represented as the infinite power series kth derivative of f at the point a divided by k factorial multiplied by x minus a to the k. So f of x can be represented as a power series centered at the point a with coefficients determined by this expression. And this holds for absolute value x minus a at most r. So this formula here, this expression for f, will be very important, and we will refer to it as the Taylor series of f at x equals a. So this formula is named after Taylor, the mathematician who arrived at it sometime in the 17th century. It has an important special case when a equals 0. This formula here becomes f of x equals the sum k from 0 to infinity f kth derivative at 0 divided by k factorial times x to the k. And this equality holds when absolute value x is less than r. This special case of the Taylor series formula will be called Maclaurin series. Again, after the person who arrived at this expression independently of Taylor at about the same time. So both of these formulas will be very useful, and their usefulness can be immediately seen by knowing the function and its derivatives at a point, say at the point a. We can express f of x as a power series centered at this point a. And there is the particular case when a is 0, and that is when we obtain the Maclaurin series. A very important point we must emphasize before proceeding on to examples and the justification of the statement of the theorem is the following. We must emphasize that this formula holds if, and this is an important if right here, f of x can be represented as a power series. So you're making this important assumption. You're saying, okay, let's say my f of x can be represented as a power series, then I'm going to be able to obtain the coefficients of this power series using these two formulas. So this is a very, very important detail right here. In general, one would have to show that a function f of x can indeed be represented as a power series, and only then can you proceed to use these formulas.